All right, so let's get started. So this is the last thing that we covered last time. And what we said is that there's an allowed set of scattering vectors. So when you have your system, let me bring this back a little bit. You will have each unit cell has some atoms in it, right? And then you have incoming radiation. And then each of those little unit cells that has some atoms in it is going to be scattering the radiation. We all agree on that, right? Each of the atoms, each of the electrons, they all scatter radiation. But then what happens is that some of that scattered radiation, let's say one of the scattered radiation from this guy and the scattered radiation from this guy will cancel out and you won't see anything because they interfere destructively with each other. And you move it a little bit at an angle, and then those two guys are back in phase with each other, so they would scatter again and put a constructive interference, and you would see patterns coming out. We also said that the requisite for this scattering to happen is that the scattering becomes intense, is that there's going to be a small number when you have this e to the negative I q dot r. This q is just a discrete set of values, and they turn out to be the vectors that give you the g, a set of vectors from g, data with a set of vectors from r, and this was our real space lattice and the reciprocal lattice vectors, right? When you have those two combined together, you get zeros, 2 pi's, 4 pi's. By definition, that's how we build those G vectors. So you found reciprocal lattices in the previous homework already, so you have played with them. So you have a discrete set of Q vectors that are gonna give you the constructive interference that we would see either in film or computers detectors, computer screens, right? And everything else is not gonna do squat because it's not at the right angle. Make sense? All right, so that's where we start now. But all of the electrons are in the systems are scattering out. It's just that they're scattering and they get canceled by other scattering because they're too noisy between each other, so you don't see anything on your detector. But there's a few that are reinforcing each other, and those are at the right positions so that the angles make that 0, 2 pi, 4 pi. And you start adding together e to the 0, e to the I2 pi, exactly, e to the I n pi, where n is some integer. And those are the allowed scattering vectors. So you might think that basically the crystallographers, what they do then is that they look at this discrete values, right? I mean, if I was a crystallographer and I had to invent this, what I would do is that I would look at those scatterings that are happening from a crystal, then figure out what would be the reciprocal lattice vectors that let me do that. The G and the R, I know how to build them. I know how to build them from R to G, right? So build those values and then say like, oh, I know what the reciprocal lattice is. I'm gonna Fourier transform all of this information that I have from my scattering. I mean, I like doing Fourier transforms. That's part of the work I do all the time as a condensed matter theorist. And then once I Fourier transform, I'm gonna get all of the structure of the crystal, all of the real space, the structure of the crystal. But it turns out that crystallographers are more clever than that. Or most crystallographers, maybe there's a few that do this, but most crystallographers don't do that, especially the ones looking at traditional crystals like the ones we're using in condensed matter physics. Maybe biophysics people do the Fourier transform still, but I mean, you guys know that they make crystals out of proteins, like the DNA crystal, right? And then they figure out what shape it has based on those, right? So that's what a biophysicist might be doing, but not the crystallographers that working condensed matter systems. What happens then is that, and this is why I think is clever, what they do, just look at the left picture as a reminder, because we did this, it feels like a long time ago, but it's because of the ice storms that we haven't had enough classes in a row. They look at these planes actually, and you see that these are the Miller indices that we already covered. And this Miller indices is what you see actually. So crystallographers in condensed matter systems, what they do is that they look at the crystal planes, and these crystal planes are going to give you those G index, and then you figure out what you have. These crystal planes are ordered. So you're going to find that when you have a system and you look, is this crystal plane showing up in my, is this Miller in the index, are the planes in this Miller index showing up? Then you can find those on your crystallography data that you get out of the system. How many of you have taken XRD? No? You have? All right. Just you? Nobody else? All right. So we have a crystallography X-ray machine, an XRD machine, up on the 5th floor in the undergraduate teaching lab. I didn't make you do that, you guys?
We did a little bit at the very end.
Okay. Somebody took it as their project, so they learned how to get those out of the data. But I think it was just 2 people, but not you 2, right?
Right.
Because you guys came in through, was it during COVID that you took my class?
No, it was semester before.
You took it during COVID and you took it the semester before. Okay. Yeah, so then there was no chance to do it during COVID. But this is something that people can do, that, right? They look at these Miller indices, and now this Miller indices, for instance, this is the 111, it was H, K, and L, and that H, K, and L are the things that go here with the reciprocal lattice vectors. So just like the R has A1, A2, and A3, the G is going to have B1, B2, and B3. And instead of being N1, N2, and N3, it's going to be H, K, and L. And those Miller indices is what crystallographers look at. They find what those integers are, and they tell you what crystal plane you're looking at in that peak, and they can figure out things like what is the lattice spacing of the system, which is really important when you try to figure out what thing you grew. How big is the crystal unit cell? So they give you this spacing. So if you look at the 100 planes, they're separated, and that's the A1 direction. And that's one of your definitions for the unit cell, A1. And you can look at the other indices and so forth. So what I wanted to do is first give you a review on Miller indices. I know you guys got it already, but it's been a while, right? So let's say, for doing things faster, I brought this thing here. And what I want to do is the following. We have A1 in this direction. Then for this case, I'm going to make A2 in this direction. And then A3 is in this direction. Okay, questions? So this is a cubic lattice, right? And then I make this quad, and this goes with A1, 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 distances right here, A2, but this is cubic, so there's just the same thing. So the distance from here to here is A, the distance from here to here is A, is the same thing. So now let's look at a plane, right? Let's say that I wanted to draw a crystal plane that was the 320 plane. This is a simple cubic. And I want the 3, 2, 0 plane. This is a 3, so my plane, because this one is 0, do those planes intersect? Let's say I have a plane coming out of this direction right here, right? Does that plane intersect with the z-axis, A3? No, sir? The 0 tells you that it intersects or at 0 or that it doesn't intersect anywhere. No intersection? Exactly, right? It intersects at infinity. Right. And then A1 is going to intersect at 1/3 and A2. All right. So another way to look at it is this plane, where does it cross the axis, right? So let me do this on the side. We're looking from the top, right? And this is, now this is from the top. This is going to be A1. This is going to be A2. And then we could have basically my planes, because of that, they're going to look like this, right? Like that. They keep going like that. Does that make sense? So for instance, if I have a plane, it's going to go 1, let's see, where do I want it to go? Well, the first thing is that the one axis, we could put that there's one right here, intersecting through here. And remember, it's a straight, right? Intersecting with a, it doesn't intersect with A3, so it's just a straight plane. This one's easy. And then it's going to intersect over here. So the one that goes with the one intersects this one right here. And this is one of those planes. And then we can draw the other one. We invert the fractions, and now we have, hold on, did I mess it up? I think I did. Huh? Yeah, it's the opposite. Poop. All right. So it goes from 1, 1, because I have 3 halves over here, right? What I did is 3 halves, but I don't need to do 3 halves. I need to do 2/3. Right? You guys see that? So I did 3 halves. No, this is not right. It should be 2/3. So it's this one. Right? So let me start again. It's a good thing I made a bunch of copies. So we have A2, A1, A3. We want the 3 halves. Yeah, we have the 3, 2, 0 planes. So if we're right, we want one that crosses at 1. The one that crosses at 1 would also cross at 2/3. So there's a plane that goes from here, and let's say that this was 2/3. And this is the first plane. That's one of the 3, 2 planes. And then we just keep going, right? And for instance, there's another one that crosses at 3 and at 2, right? So that's the next one. And they're the same separation. And then we do the next one. And then we keep going like this. And you can do So this is this one, this one. You can figure out if this one was 1 and this is 2/3, this one is 3 and is 2. You can do the next one that should be, let's say, at 4, right? So what would be the value at 4? Sorry? No, so this guy crosses at 4. Let's see. So this one crossed at 1, then at 3. And we can put, like, what are these planes passing across like this in this direction? Right. So you have to look at where it crosses on this end over here. Right. So we do 6. 1, 2, 3, 4, 5, 6. Then this one is 4. Right. Something like that. And this is another plane and so forth. Does that make sense? We can do all the planes that we want. And all of these planes are going to be planes that do the satisfy, because they're inside of G, the set of vectors that satisfy the 0, 2 pi, 4 pi, and so forth. Make sense? Yes, no? Yeah?
I want to know why we didn't choose the 3 1 0.
All right, so what we want to do is invert the fractions. Right, so we want to invert the fractions and then put the ones that are integers. Does that make sense? Those are the planes that we care about. So yeah, this plane, the one that crosses at 1 and 2/3, that's not the one that we want. We want to get, well, that's one of the planes. What we want to do is view from of these 3 2 planes would be such that they're in integer, so that they cross at those unit cell corners. So we want the ones that cross at here and here, here and here. So we want one of them to be an integer, at least. That's the point.
Yes. So when we
Right. So this one is 1 and 2/3, right?
right.
And then this one is 3 and 2. Yeah. So
Possible, like the first one that you did,
Mhm.
3 have 1 and 0.
Mhm.
I mean, in the previous
Right.
copy. So why can't we take that?
Yeah, so it's the same direction, but it's actually, here's the point that I was going to make afterwards. It's the same direction, but what we want is for these guys to be separated by the same distance. So now what we have here, this set of vectors, right? This one and this one, this one and this one, this set of planes, they're separated by a distance. And that's what I was trying to draw with this picture over here. Right, so the distance here, right? This distance and this distance is the same. So if they're integers, if we go with the least common, the one that has the least common denominator, right? So we have 3, 2, 0, right? So that's the thing that we want. We want to get an integer in there. And then this distance becomes something that we can calculate.
Or probably we want a fraction that is not 1. I don't know, that is
Right,
only
exactly. So there's only one that is below 1. Exactly. So we want these guys to be such that if we look at it over here, so let's say that we were looking at this guy right here, and he has 1, 2, 3, And then it would be like here and here, right? So basically what we're doing is that we have this plane and then this plane, and then there's another plane that keeps going in this direction, like that is supposed to be parallel to those. And then from here to here, we have a distance HKL. So we have the Miller index. Our Miller index is this one. And then this is looking down on the z-axis, right? That's the planes that you would show. So we have those planes. And what happens is that there's a vector that is normal to this plane. So for instance, there's a vector going in this direction. This is a normal perpendicular to that plane. This normal vector is actually called G H K L. And this is if we look at this vector, the magnitude of it, so this would be the one that is normal, right? The unit normal. That's why it has a little hat right here. But then if you look at the real vector, not the direction only, this one is going to be given by 2 pi, and then that distance, HKL, that we talked about. The magnitude of this vector is inverse of the distance between those two planes with the 2 pi factor in there. Does that make sense? So this vector has a direction, is perpendicular to the normal, to the plane, is the normal of the plane. And then it has a magnitude that is the inverse times 2 pi of the distance between the planes. So let's go over the math on this. I'm not gonna do a proof. Exactly. Is one of the reciprocal lattice vectors. Because this G vector, right, it has HKL, and it's going to be HB1, KB2, LB3. All right, so let's look at this. Just not a proof, but it's more like show that it works for one of the planes, okay? So I don't know what these are called. It's not a proof. What is it called, Cosmo? You're the math major, right?
No, that was Gary.
Oh, dang. Okay. So it's absence of a proof. Let's call it absence of a proof. So we're going to have, for a simple cubic, what we want to do is show first, what is this magnitude? And remember, this is simple cubic, right? So how do we get the magnitude of a vector? We take the square root of the dot product. This is simple cubic, so I know that all of the magnitudes are of the size of the vector, right? Its reciprocal lattice is 2 pi over a, right? So that's the magnitude of each of them, but then they're squared. And then the things that go on the inside is B1, B2, B3, but they're dotted. And so you have, so should I write them out? Or just put the, all right, let me write them out. So it's HB1 plus KB2 plus, no, sorry. B1 direction, B2 direction, L, B3 direction, and they're not, This 2 pi a takes the magnitude of this distance, right? All of them are the same. And this is dotted with the same thing. So then you will have B1 dotted with the B1 unit vector. So that gives you an h square, not h bar, h square. We're not in quantum, right? And then B2 right here just gets dotted with the B2 on this side. So you get the k square and then the L square. All right, questions? So that's the magnitude of my vector.
For body centered and dick centered.
Those vectors change, but they're still the same. So this is magnitude. So now if I go like this, this is the unit one just to get direction. This is going to be the same as the original vector HKL divided by this magnitude that we just calculated. And what we get is that there's a vector H x hat plus ky hat plus LC hat divided by h bar square. No, not h bar square, h square, k square, L square. All right. So that's for a simple cubic that always works out. This one is kind of complicated right here. So let's go with the simpler one. Let's do the simplest ones first. And then come back to this one right now. And then we can look whether those things make sense, that this is the distance between them and such. So the easiest to do would be one, where we have A1 right here, A2, and A3, right? And in this case, we're gonna make it so that it crosses one, and then it just keeps going at one. And then it crosses, then we have the set, right? Then this one is gonna cross right here, and it goes like that. 1, 0, 0, right? So this is the 1, 0, 0. Because this set of planes, the first one the one that crosses is the 1, 0, 0. And remember, they're all the same plane, right? It's just displaced by a distance between them. So now, if we look at this guy, this is 1, 0, 0. What would be the distance? Did I write the formula for the distance? Dang, I didn't write the formula for the distance. Right? All right. So in this case, the formula for the distance 1, 0, 0 is going to be A divided by 1 squared plus 0 squared plus 0 squared. So what's that distance? A. What is the direction of the normal vector? So you can see this one is 1 on the bottom, right? And then it would be 1 in the x direction. So there's a vector coming coming on this plane in this direction, that's your G vector, the G100. So that's easy, right? And then you can see that the distance is just A because they're separated by a distance A. All right, let's do another one that is a little bit more complicated, not too much. So now let's say that we had, again, this is a 2, a 1, and a 3 down there. In this case, it's going to cross at 1 and 1. So that's one plane, right? Then it's going to cross at 2 and 2. And then 3 and 3. All right, questions? So if we look at the distance between planes, this is the 1, 1, 0, right? Well, 1, 1, 0 plane, the set of planes in the 1, 1, 0. If we look at this distance, this is A over a square root of 1 squared plus 1 squared plus 0. So the distance between planes is A over square root of 2. Salud. If we look at it from the top, you'll see that that's true too, right? Because this is this diagonal versus this diagonal. So it's not 1 anymore, and they go like that.
Similarly, for the 1, 1, 1 matrix, distance separation of A over.
Right. So now let's make the hardest one. Well, not really the hardest one, but the one that has the most numbers in it. So this one is going to cross at 1, 1, 1, right? So it's like a little triangle here. So that's one of the planes. And then we have the next one that is going to cross through here, but it's also going to cross through here like this. And then it crosses through here like this and so forth. And it keeps going, right? What's the vector coming out? It's coming out in the, this is the 1, 1, 1, and it's coming out in the x hat plus y hat plus c hat. And then these are unit vectors, so you have to divide by square root of 3, right? So what's the distance between them? So we look at the 1, 1, 1. We have A on the top again, and then 1 squared plus 1 squared plus 1 squared, and Cosmo, that's what you were looking for. Questions? Questions at this point? No? All right, so let's go back to this guy then. This is our friend over here. Yeah, now I remember why I didn't tell you what the D vector, the length of it was. Because now we're going to figure it out for this one. And now you saw how it was done for the 1, the 1, 1, and the 1, 1, 1. 1, 0, 0, 1, 1, 0, and so forth. So in this case, we have that this is the D 3 to 0. And in this case, we get A divided by a square root of 3 squared plus 2 squared plus 0. And if we do the math, that's going to be A divided by the square root of 13. Make sense? And then this normal vector is the normal vector 3 to 0 to this plane 3 to 0, 3 in the x, 2 in the y hat direction divided by the square root of 13. So the distance between planes is A divided by the square root of 13. We have that normal vector coming out of the thing. And that's what we were thinking before, right? That's the distance between those guys right here, this guy's right here, and so forth. So that's the things that's the Miller indices. That's what that covers how to do things with Miller indices. How do we get that distance between planes? The full set of planes, the ones that passes through 1/3, 1/2, right? And all of the possibilities that we have. Questions? No? All right. So then let's go back to X-ray scattering. For X-ray scattering, I had told you about Laue and how he came up with the work to be done. And he figured out what it was that he was getting, right? So that was Laue. The persons that came out with how it works for these planes were Bragg and Bragg. It's actually father and son. So now the son figured it out, basically figured it out. The dad helped him with something, and then the dad went and published it. And then he put on the paper, and I thank my son for some minor help or something like that. Nice family, yeah? What would you do if your dad did that to you? So yeah, he took the homework and just put his name on it. Well, anyway, the credit should be to both Braggs. So at this point, we're not scattering from like before we were thinking of atoms, right? Or of the electrons in the atom, basically. And we had the form factor and we were looking at this unit cell. The thing that we're doing now is that we have a scattering wave that is coming out of the HKL planes of the crystal. That's the Bragg diffraction thing. So the son of Bragg was really sad about it. I don't think he ever spoke to his dad again. So we have a plane now. Let's say that this was our plane. The incoming radiation is going to be incoming from here in this direction. At this point, there's a Ki incoming. And then we have that there's an angle theta right here. We have a vector coming normal to this plane. What's the name of this vector? Is that guy, right? The reciprocal HKL vector. And then we have that this is the outgoing of that plane radiation is being scattered and it has a direction KS. That's the vector coming out. We can say that there's an angle here. Let's call it phi. Questions at this point?
I guess the one thing you know that might have with that reflection, phi and theta are not necessarily equivalent.
I'm not sure yet. Let's figure it out. So I'm just gonna take this vector and put it over here, okay? Make sense? That's the negative ki. Negative ki. And if I do that, then I can give you this additional vector that goes here. This vector is the vector q. So this q is ks minus ki, just like before, right? Questions? All right. So we have radiation. It's coming into the plane at an arbitrary angle, theta. And then it's scattered. It has a scatter wave that is coming out of the plane at some arbitrary angle, phi. So we have the allowed scattering conditions. So this is from before, right? This is Laue. This require that you have that this scatter wave vector q be ks minus ki. And that has to be exactly the same as this HKL for that plane. So what that means is that the direction of Q, right, must match the direction of this vector right here. So what would that tell you about the angle? If they have to match, this Q and this G have to match in direction. Exactly. Right. So exactly what you were thinking, right, Cosmo? They're the same magnitude of the angle, right? So incident and reflected angles are equal. And this vector addition right here is actually an isosceles angle, which is not what I drew right here because I was exaggerating the two vectors. So if you look at it from the optics, this is the law of reflection, right? All right. So the scattering constraint, we can write it to we can rewrite that constraint into the following, and we're just going to multiply by Ks and rearrange things, and we would have Ks, one vector dotted with Ks vector is equal to Ki plus GHKL dotted with Ki, the vector plus HKL. If I do that, then I have Ki dotted with Ki. So I have the magnitude Ki squared. Then I would have twice Ki plus that Ki G twice. Dotted with HKL. And then I have the vector G magnitude because it started with itself. When we have elastic scattering, and I remember you can have non-elastic scattering too. Elastic scattering, that's where energy is conserved. Then this magnitude and this magnitude are going to be the same. And therefore, we're going to get Ks magnitude is equal to Ki magnitude. They're just in different direction. And we know that this is the wavelength of the light, if it's light. So, oops, if we do that, we're going to have, there's a Ki square here, there's a Ki square here. And we can just move this guy to the other side. Those two cancel out. And we get J HKL squared is equal to -2 Ki dotted with G HKL. Questions at this point? We're just doing math, right? So it's okay if you guys don't have questions. So then we grab that guy. If I have that, I know this guy, right? Ki is 2 pi lambda. Then I can put 2 pi lambda here. Then I have the vector, the magnitude of this vector, HKL. And then I have to look at the angle between G, HKL, and Ki. So you see that the angle is not theta, right? It's not theta. It's 90 minus theta, right? So if I'm dotting those two guys, the next term would be cosine of the angle between them, but the cosine, the angle between them is 90 minus theta. And that's just looking at this vector versus this vector, right? That angle. So once we have all that, we then have that HKL squared, it's equal to 4 pi lambda. I think I lost my minus in my notes. There has to be a minus somewhere here. Then this magnitude of the vector HKL, and then cosine of 90 minus theta is the same as sine of theta. So we have 4 pi lambda, this, which is the same as over here, sine theta. Questions? So then I can rewrite all of this, and since from the Miller index discussion, we had that this guy is equal to 2 pi divided by DHKL. That's the size of the vector, right? We now get that we take the lambda to one side and we get 2. There's a 2 pi right here, so there's a 4 pi over here. And this is the Bragg diffraction law. So that's something that you might have seen before. This is how it applies to crystals. Yeah, Cosmo?
In fact, I might have seen this work with optical gradients.
Yes, exactly the same thing. The gradient, the grids, not grids, the spacing between the slits, yeah, kind of thing. So you have seen this. Yep, you have seen it. So we have that this is the scattering condition, and that leads us to Bragg's law. So let me give you another picture, an updated version of this one, right? So in this case, we're gonna have a plane here. And let's say we have another plane here, and then there's another plane down here, right? We know what the distance between the planes is. This is this DHKL. Sorry?
Oh, well, it depends if you're looking for.
No, just the first surface, I think. Number of the surfaces, so that's where the N comes in.
Right. Number of surfaces is where the N comes in. Yeah, but in this case, we're scattering of one plane. Okay, so this is the distance. We have different planes. This is the distance between the planes. We would have, let me use the same color as before, incoming radiation here. This is theta. So that's my Ki. Remember that the source of the radiation, whether it's X-rays or neutrons, is coming from far away. So we have, I'm gonna put it in the same point. So there's this direction. We have that there's radiation coming in this direction like this. That's incoming radiation, right? And this radiation gets scattered in this direction. The scattered radiation has also an angle theta right here because it's the same angle as we discovered. Then there's a vector G that goes out in this direction, HKL. And finally, we have that. So let's say that just to have direction, right? This is not a continuation of the vector. This one goes in this direction. This one goes in this direction. All right. So I have this being reflected, right? And if we look at this guy going in this direction, and the angle between these two right here, this one and this direction, if I had projected it down, this is actually 2 theta. So I'm just making this because later we're gonna see 2 theta coming into the picture. All right, so we have incoming radiation is gonna get scattered. This incoming radiation, which is in the same direction as this one, gets scattered too. These two guys are getting scattered at the same time. And what we wanna do here is when you're doing the XRD. So again, if you're doing XRD, just like what we have in the 5th floor, there's other machines like that on campus. But what that one does is that you grab powder of your sample, you make it a really fine powder, and then you stick it in a little, it looks like a little tiny puck. And then once you put it there, you cover the whole puck with that, or maybe cover the bottom of the surface. Then you have X-rays coming at it. X-rays, let's say, coming in this direction, and then you have a detector that does this. So what you're changing is actually this angle 2 theta right here with the detector as the detector moves. So that's one type of diffraction experiment on XRD. And what you have there is a powder diffraction method. In that technique, you have a beam of monochromatic X-rays. So the X-rays are generated by usually a copper filament. I don't remember what the one upstairs is. It's either copper, calcium, something like that. And that generates X-rays. You put the X-ray source, you put a high voltage on the metal, and that generates X-rays. So it's monochromatic because you have filters so that there's only one wavelength. If you have more than one wavelength, then this is gonna be all over the place. So you wanna make it as small in width of what wavelengths you have in there as possible. That improves your resolution. Then you have this powder, which is that you pulverize the material by putting it in a mortar and pestle. You have this little fine powder, it's a pulverized material, and then you could rotate the material through an axis, or in this case, you can rotate the detector through an axis. And that's what you're getting. Because you have a bunch of little crystallites in the powder, you get a bunch of diffraction at particular angles. So in this case, there's a random direction of thousands, maybe millions of crystallites. So you have Bragg planes in all of the directions in the powder, because they're pointing in different directions. They're not oriented with respect to each other. They're randomly oriented. And then when you're moving the angle through the angle, the detector, what you're doing is that you're picking up some of the allowed angles, and only the allowed angles are coming at you. And then you record things as a function of intensity, as a function of this angle. So for instance, this is the incoming radiation. That's not gonna change. And if your detector is over here, that's the one that gets reflected. If you're down here, then your incoming radiation would be coming like that, right? So if you change this angle, you change this angle. You go from here to something like this. And you're changing that angle together. And then you get all of these Bragg peaks to come out, and you get to see the intensity being produced. And some of this, only some of this are gonna, at a particular angle, are gonna come up, but you have a bunch of them, and you're bound to pick up the right ones because you have a bunch of difference. There's another method to do this. That's something that they're doing the Myers group too, where they go over there to with a single crystal to venture one. Then they put the crystal in there, and then they try to align the crystal to some plane, and then they rotate things around it. It's called a goniometer because it does a weird rotation to get you the 2 theta. You seen it? Anybody else? You seen it? So those will give you the same thing, but that's a huge crystal, and you have to align it so that you have it in the right axis, and then you rotate around that axis. So those are more complicated, but it's the same principle. So the powder one is the one that is used all the time. All right, so once you have that, what you would do then is, for instance, let's say that you had sodium chloride. So you guys know this is a cubic crystal, right? So if you have sodium chloride, this would be the intensity over here. And this is the 2 theta angle. So you don't start it at 0. They usually start around 20, these experiments. You can go lower, but it's usually around 20. So here we would have 20, 40, 60, 80, 100, maybe 120 right here. You also cannot go all the way to 180, right? Because that would be on top of the radiation source. So, the XRD that you're gonna find for, let's say, sodium chloride might be when you do the, well, when you do the XRD, you get a bunch of peaks and you leave it there for maybe 20 minutes, 30 minutes, an hour, depending on how much sample you have. And then you're gonna see that some of those peaks start growing. So they have a different width, but they could be going around like something like here, there's a little peak, and then there's a huge peak. And the peaks are like on top of each other sometimes, and they're hard to guess what it is. But what crystallographers do, they might be another peak right here. They might be a tiny little peak here, and then there's a bigger one. And then there's another peak around 80. And then one in between there, and then another one right here. What crystallographers do then is that this is what where peaks should appear. They have calculated for a particular unit cell. And then maybe the data looks like this. And actually here, it could have a lot of noise in this direction somehow, and it just looks weird like that. So this is the red one, is kind of like what your data looks like. But then you have a database where you have calculated all of the where somebody has calculated all of the possibilities, and they know what sodium chloride unit cell is, because that doesn't change, right? Even if you have Himalayan salt, it's going to have the same unit cell as normal salt. The Himalayan salt just has some curative properties, right? No, you guys never heard of that?
Right. There would be certain degrees of impurities that are partly responsible for the color that it is.
Yeah, it's impurities. It's nothing to cure you of anything. But some people believe that they can cure you of things, and then they pay a lot of money for it. And as far as I know, they taste different.
Probably a little bit.
I never tasted any difference. They look pretty in pink, but I never had any different in taste. So I'm not gonna pay 10 times.
It's more by nature.
Yeah, so maybe my tongue is not as good as those guys that sell it. So anyways, they know this, and then they have these peaks, and you can figure out what you have based on the positions of the peaks. So for this, you would say like, okay, you tell the program, I'm gonna use a copper source for my X-rays, is using the kappa alpha transition. And then based on that, you know that the wavelength of the X-rays is 1.54 Armstrong. So this is something that our instrument on top, that never changes, right? Because you're using the same source. So that's something that is with the instrument. And hopefully it doesn't change, because if it changed, then everything is screwy. And then you have all of these things right here, and the allowed peaks would be that this is the 200 Miller index, and that's the one that is refracting. They would know in the database there's a 220, maybe this one is 222. This is 420 and 422. So that's what those peaks are, and that's what the database knows based on the size of sodium chloride. Knowing that this is the wavelength that you're using, 1.54, they stick it in there. And because it's sodium chloride and they know the size of the unit cell, they're able to get those numbers and say like, oh, there's a peak that should be here, 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 here. And if you see those peaks, you know that you have sodium chloride or something that is very close to sodium chloride. Questions? So you could have another crystal, different. This is intensity 2. I'm going to use the same angle as above, 2 theta. And for this one, maybe your data is that you're gonna have a huge peak right here, then some tiny ones here, then another bigger one. Well, this one is way bigger than this one in the simulations that I was looking at. And then you look at peaks, and then there's a bunch right here, different sizes, some are bigger than others. So it turns out that this would be the case for, so this is sodium chloride, and this one would be cesium chloride. And according to the simulation, this is the 110 plane. There's 3 little ones, and then the 211, 220, 310, and so forth. So now, these are not the same exact structure, right? But you can see that the 220 for sodium chloride is up here, whereas the 220 for cesium chloride is shifted in one direction. So if you see a shift, is you didn't change this thing, but maybe you increase the distance between things. You see a peak at a different angle. It could, if your angle shifted, is because you have a bigger crystal. So let's say you were making sodium chloride and you had actually an alloy that is sodium chloride and sodium bromide. And assuming that it's still in the cubic, it would be displacing, because it's a bigger unit cell, because bromide is bigger than chloride, there would be a displacing of these guys. And maybe because of that displacement, you can figure out what is the unit cell of the system and by how much it grew. So those are the parameters that in the experiment you would be looking at. So these are from some powder crystals with some of the Miller indices put in for some of this, according to computer software that I was using for putting this thing. There's a question for you guys. Here you see a 110. There's no 110 up here. What happened to it? Here we see 220, 220, 200, but not 211. So you see there's some that appear here, but not here. Why is that the case? Can we figure that out? So we're seeing reflections that are missing in the X-ray if we have a cubic lattice. So far, what do we know? We know that all Q that are equal to some HKL reciprocal lattice vector produces constructive interference. We know that these guys interfere with each other. That same plane interferes with itself. All of these planes are going to interfere with themselves, and they have the right distance. And basically, all of these guys, because they're the right distance between them, they're all interfering at this particular angle constructively. So what that means is that we had constructive interference, and we could look at that means that we have a crystal structure factor at some angle that depends on from some planes at some angle, and that the structure factor is equal to n, the number of cells that we have. So we're going to have a maximum in the structure factor of the crystal if our Q value is equal to one of these plane vectors. And we all agree on that part, right? So now the question is, I have a structure factor for sure. Does that mean that I have intensity? Remember, you don't measure structure factors with X-ray diffraction. you measure the intensity of the X-rays on your detector. So how about the intensity? How do we do the intensity? Well, for the intensity, we get that there's a formula for it. This is the intensity for this vector. That's going to be related to the square of the total electromagnetic radiation scattered. The intensity scattered is equal to the total. And what we have is, going back a couple of, I think 2 lectures, we will have the number of unit cells that we have, the scattered radiation. This is the total scattered radiation. This is the scattered radiation. Let's say we had the same type of atoms here, so that they're all, we can take them out of the summation. Then we have something that is this little f. You guys remember what this little f is? And then the structure factor. You guys remember what this little f is? I'm pretty sure I covered it, but or did I not cover it? Let's look up over the notes. Yeah, I covered it right here. So we have a structure factor. And we also had that this is the little f is for the cell. And this little f is the one, this is the specific arrangement of the positions of the atoms in the bases. So this little f is the one that tells you where the atoms are located in your unit cell. So if we maximize this S, if I maximize this F, sorry, if I maximize this S right here, which is what we could do, we maximize this S because we're in the right, in a Miller index plane. But what about this guy? We haven't talked about this one yet. What if we're maximizing this one, but then this one ends up being 0? I mean, this is not going to be 0. This one is not going to be 0. This one is maximized, but we still could have that this guy is 0. And that's actually what happens when you have this is the, so this one is called the static structure factor. That can be maximized. And this one right here is called the cell form factor. And this one could be 0 for some position of atoms. All right, so that's where I want to stop because we have 1 minute left, and ask if you have questions. And then we'll do some of examples on Tuesday. Questions? All right, another thing that we have to do, we're almost done with the basics of solid state that you would cover in a solid state class, whether undergrad or grad. And then we're getting halfway through this into getting into the things that I like most about this course, which is where you guys learn about the techniques. So look at your book. There's materials and there's techniques. I want each of you to present a material and a technique. Figure out what technique you like. Maybe some of you like pulse laser deposition and you want to present about pulse laser deposition. Maybe you want to learn something new, right? Because you already know pulse laser deposition. And if you look at the book has like maybe one paragraph on some techniques. And if you go and look up a technique, it's going to be more than one paragraph. So I don't know what technique you choose. Choose something that you want to learn about or that you're an expert on. And then what we're going to do is that we're going to have 10-minute presentations for each of this. So it's not a full hour, okay? It's not even 20 minutes, 10 minutes. Don't take too much time because there's a lot of us that want to talk. So look at the book. If there's a technique that you like that is not on the book, you can also present it. But there's different things. Like for instance, if some of you are interested in density functional theory, I already heard from Cosmo that he wants to do that one. If you're interested in carbon nanotubes, I don't know, what is your favorite material, Paul? All right, you're interested in SIGs. You want to tell us about SIGs and its uses. It's not on the book, but you can clear it with me and I give you permission to present that. Casper, what's your favorite material?
No, I don't know if I have one off the top of my head.
All right. Dirk? Ahmed? Should have said zinc oxide, because otherwise Dave is going to be mad at you. What's your, Mr. You don't have any? No? Nahi? All right. Cosmo?
I'm actually thinking about some of the organic photovoltaics that we looked at. Would it be all right for me to pull back?
There's molecular, yeah, there's molecular crystals in there in the book. So you can look that up. And organic systems is one of those.
Yeah, I figured it'd be a nice showcase for the undergrads to see what it's like.
Well, I think it's for everybody because we don't have experts on a bunch of different materials here, right? So, Nikita, what's your favorite?